Hello students, welcome to another session, and this is almost last topic of this vector algebra and very important from the point of examination, that is scalar triple product. So let's begin with the scalar triple products. So the scalar triple product of three vectors, suppose A, B, C are any three vectors and their scalar triple product is denoted by in this form, that is in square bracket you have to write vector A, B, C, either you put comma or you can write straight away. So the scalar triple product is denoted by in this fashion and it is defined as vector A dot B cross C. This scalar triple product has got its own geometrical application. So this is one of the most important topic. So let's understand with the help of geometrical concept. So the scalar triple product of any three non-zero vectors is defined by this vector A, vector B, vector C is equal to this. This is also called a box product because the representation is in the form of a box brackets or square brackets. So let's understand much more about this. One thing to be noted, as the scalar triple product is a scalar quantity because it is the dot product between two vectors, vector A and vector B cross C. So to be noted that a scalar triple product is a scalar quantity. And one more, it has got its geometrical application. So let's understand what is the geometrical meaning of scalar triple product. So actually the magnitude of the scalar triple product gives you the volume of the parallelepiped whose adjacent side vectors are vector A, vector B and vector C. So this is one of the important application of this scalar triple product. We will just see how this scalar triple product represents a volume of a parallelepiped. So this solid is called a parallelepiped, means each face is in the form of a parallelogram. Okay, and vector A, vector B, vector C are these vectors are they are the adjacent sides of a parallelepiped. Okay, so let's understand how the volume of this will be this triple product. Let's prove this. The proof is for those who are interested one. So let's see. So consider a parallelepiped A, B, C vectors as their adjacent sides. Means this is your vector B, this is vector C and this is vector A. And we are interested in volume of this parallelepiped. So as we know that the volume of parallelepiped is given by base area into height. Okay, if you multiply this base area by its height, you will get the volume of this parallelepiped. Okay, so the volume of this parallelepiped is given by area of the base into height. Now clearly we know that the area of the base, it is in the form of parallelogram. So as we know that the area of the parallelogram is the modulus of or the magnitude of cross product of these two vectors. Okay, because the adjacent sides of this parallelogram are vector B and vector C, and as we know that how you can find the volume, the area of parallelogram, it is the magnitude of the cross product of adjacent sides. So the area of this base is this magnitude of vector B cross C. Now we want height. What is the height of this parallelepiped? So if you find the height, then the product of these two gives you volume. So now our aim is to find what is the height of this parallelepiped. Okay, so this distance between these two parallel sides is the height of this parallelepiped. and which is nothing but it is this height, okay, from here to here. Okay, now this height is nothing but what? It is, and which is nothing but projection of this vector on this, projection of vector A on this vector. And what is this vector? It is vector B cross C, because we know that B cross C is a vector which is perpendicular to both vector B and vector C. Actually, cross product of these two is the vector which is perpendicular to vector B and C. So this is the perpendicular vector to both B and C. If you find projection of this on this vector, means this distance. Projection is what? It's the distance between the foot of perpendiculars. Okay, so now if you find the projection of this vector on this vector, then that is your height. So let's understand. Okay, so here is a parallelepiped and base area is, it is magnitude of B cross C, and we want height. So let's reverse it. So I rotated it in this fashion, and we want actually this distance. Okay, so this is the height, and which is nothing but the projection of this vector A on the vector B cross A. This is your vector B cross A, and this is your vector A. Now we want the distance from here to here, that will be the height of the parallelepiped. Okay, now how will you find project? This is what? This is actually projection of vector A on vector this. Okay, and we know that how to find projection of one vector on the other vector. Okay, so here is the height is nothing but it is projection of vector A on vector B cross C, and we are interested, the height is always positive quantity, so we take mod of this projection. Okay, so projection of vector A on B cross C, vector A on B cross C is this length, and which is nothing but its height. Okay, so now by the regular definition of projection, how will you find projection of vector A on vector B cross C? It is vector A dot vector B cross C by magnitude of vector B cross C. Okay, we have done it earlier. Projection of one vector on the other vector, hence projection of vector A on vector B is vector A dot vector B by magnitude of vector B. So in the same fashion, here B stands for this B cross C. Okay, this is your vector B and this is your vector A. So projection of A on B. Okay, like this. Mod is because we want height, so height has to be positive. So in order to get the positive, we have just taken mod of that of magnitude of that. Okay. Now as we have parallelepiped volume is area of the base into height, and as we know that area of the base is this magnitude of vector B cross C, and we have the height here, height is this, so substitute here, and you can cancel this magnitude of B cross C, magnitude of B cross C, you left with this quantity. Okay, so this is how the volume of the parallelepiped is given in terms of this scalar triple product. So geometrically, the magnitude of the scalar triple product gives you volume of the parallelepiped. So remember this. One thing to be noted, when you press this parallelepiped so as to form a plane, means if you press this, all the vectors, vector A, vector B, vector C, they all lie on the same plane, then the volume becomes 0. In such case, we can say that the vector A, vector B, vector C will be coplanar. So if you ask to show that the three vectors are coplanar, then you have to show that their scalar triple product is 0, because the volume in such case is going to be 0 when the three vectors will be on the same plane or they are coplanar. So one of the important point to be noted. So let's move. Now determinant form of a scalar triple product. So whenever you will be given three vectors in their component form, means in terms of I, J, K, then what is its scalar triple product? So let's see here. Here vector A, B, C, they are given in terms of component form, that is in terms of I, J, K. Then see here, what will be B cross C? As we have studied earlier, the cross product of two vectors in the determinant form is given by this I, J, K determinant. Second row is B1, B2, B3 and third row is C1, C2, C3. And expand this, you will come up with this. Now you have to find dot product of A and this. Let's see here. This is your B cross C, this is your vector A. Now you have to find dot product between this and this. As we know that dot product of two vectors is what? It is A1 A2 plus B1 B2 plus C1 C2. Means sum of the product of the coefficients of I, J, K in both the vectors. So here we have, so this is A1 and this is treated as a B1. So this into this. Next, this into this. We have minus here, so I can write minus here. Next, this into this. That is A3 into this. Okay. Now, actually this is what? This is the expansion of this determinant. If we expand this determinant along the first row, you will get this expansion. So this expansion can be put in the form of a determinant. So you can write triple product as in the form of determinant. So you have to remember, when the scalar triple product will be asked, whenever the vectors are given in terms of components, you just find the value of this determinant. Now you have to remember that the scalar triple product can be written in this fashion. Means these all three scalar triple products are equal when you write or when you change the vector in cyclic order. Look at this. Vector A dot B cross C can also be written as or equal to vector B dot C cross A, and which is also equal to C dot of A cross B. Here what is done is, here A, B, C are cyclically interchanged. Means replaced A by B, B by C and C by A. Okay. So that means the scalar triple product, this can be written as this is equal to this is equal to this. Here A, B, C are cyclically interchanged. So why it is and how it is, if you have curiosity in your mind, then just expand these determinants. Okay. So this determinant is for this triple product and this is for this triple product and this is for this triple product. If you expand all the determinants, you will get the same expression. So let's move on to the next, and we'll have one simple example to understand the scalar triple product. So here you are given three vectors, vector A, B and C, and you are asked to find their box product or scalar triple product. So as we know that this can be written as this, and which is the determinant value. Okay, so just substitute the coefficients of I, J, K and expand. As we know, the determinant expansion, and this is the final result. This is your scalar triple product of given three vectors. So better you take screenshot. So we'll move on to another example to make you much more perfect. So let's find this. You have to find the scalar triple product if these three vectors are given, and the answer is here. Understand, make your own notes. Hope you understand. Nothing is hard here. Okay, you have to take care of the positive and negative signs while expanding the determinant. That's the thing. Now we'll move on to next some of the important things. In scalar triple product, dot and cross can be interchanged. So how? Why? Let's see here. Now see here, this is your scalar triple product, and this can be written as this And as we know that this can be written in this form because the value of the scalar triple product does not alter, does not change when the vectors are interchanged cyclically. Okay, so using this, and this can be written in this form. Okay, vector C dot A cross B. And as we know that dot product is commutative. Dot product is commutative means you can interchange the vectors in the dot product. So this can be written as, you can just interchange the dot product vectors. You can write C here and vector A cross B here. Okay, so you can see here that the vectors are in the same order, whereas the dot and cross are interchanged. So you can remember in this fashion also. Okay, so for whenever it's required to change the dot into cross, so you can use this. So let's move on to next part. The scalar triple product equal to 0 if any two vectors are same. Suppose in the scalar triple product, if two vectors are identical, then their scalar triple product is going to be 0. How? Let's see here. Okay, so what we know that if in a determinant two rows are identical or two columns are identical, its value is going to be 0. So using that property, how to write in this fashion, whatever the coefficients of vector A1, A2, A3, you have to write twice. Okay, so here two rows are identical, so definitely this value is going to be 0. Suppose you have vector B and vector B somewhere, order is not important. Anywhere in the scalar triple product, if two vectors are identical, then its triple product is going to be 0. Why? Because in that case, two rows becomes identical. Okay, so wherever maybe either you must have two A's or you have two C's or two B's in the scalar triple product anywhere. So straight away you can write its triple product as 0. The reason is two rows will be identical and the determinant value is 0. So let's understand this. Okay, so look at this. The scalar triple product of this is going to be 0. In all the cases, there are two identical vectors irrespective of the order. Now we will have some important problems on the scalar triple product from the point of examination for 3 marks. You may guess some of the standard questions. So let's see here. You are asked to prove this. Very simple. The scalar triple product of this is nothing but sum of the two scalar triple products. Okay, let's understand. Just apply scalar product definition for this and expand it. You will get straight away these two terms. So here it is. Okay, so LHS is this box product, and you can express it in the form of product. That means you can write it as vector A dot of, it's a cross product of this and this. Okay, now you can apply cross product, distribute this cross product over the addition in distribute model. Okay, so you can distribute this. So B cross vector C plus B cross vector D. Now further you can distribute the dot over the addition. So A dot of vector B cross C plus vector A dot of vector B cross D. So this is nothing but it's a triple product of A, B, C vectors, and this is the triple product of vector A, B, D. So you can write it as in this fashion. Very interesting, very simple, straight away. If you have a basic ideas of a distributive property, you can prove very easily. Could be asked for 2 marks. So remember, we will be moving on to another standard example on the scalar triple product. Okay, very much important. So remember this. You are asked to prove vector A plus B triple product of vector A plus B, vector B plus C, vector C plus A is equal to 2 times this scalar triple product. Okay, so let's begin with the left hand side. So here it is. We have the LHS here, and as earlier you can put it in the form of product of vectors, that is scalar triple product, So this is your first vector, this is your second vector, this is your third vector. So you can write first vector dot cross product of next two vectors. Okay. Now you can apply distributive property for this bracket term. I can write this as a b cross of vector c plus a plus vector c cross of vector c plus a, just distributed. Further, you can use this distributive property, means distributive cross over the addition. Okay. First you have to simplify this bracket term. So this is as it is. Now you can write b cross c plus b cross a plus c cross c plus c cross a. And one important thing that I stated earlier, the cross product of two similar vectors is 0 always. So here you have vector c cross vector c, which is 0. So you can replace this by 0 and rest of the thing as it is. Okay. So this is kept as a 0 vector. So this is as it is. Now you can further distribute. Okay. You have to distribute vector over this and vector b to this. Okay. So just vector a dot of vector b cross c, vector a dot of b cross a, vector a dot of c cross a. Similarly, you can distribute this vector b over this. So you can write vector b dot b cross c, vector b dot this. Okay. So just we have distributed the vectors a and b. Now in the triple product, these are all the triple products. We have got now 6 triple products, and we know that in the scalar triple product, if any two vectors are same, then its value is going to be 0, that I stated in the last point. Okay. So here look at the triple product where you find two similar vectors. Okay. Look at this. Here in the first term all the vectors are different, a, b, c. Now in this case you have a and a, means two rows will be identical. In this case also you have a and a. In this case you have b and b vectors. Here also b and b. Okay. So the except first and last terms, all the terms are going to 0. Okay. Because in those you have two identical vectors. So you will left with this much. Now we know that this is nothing but you can write vector bca and this is your vector abca. And as I stated earlier, these two are identical because the scalar triple product does not alter or does not change when the vectors are changed cyclically. So here these two are identical. So addition of these two gives you 2 dot of, that is 2 times this scalar triple product. Okay. So remember this one of the important problem as well as proving as well as a standard result. Now we'll have one more for your practice. What will happen if this will be minus? Okay. So let's see here. For your understanding, you can work out this. Prove that vector triple product vector a minus b, vector b minus c, vector c minus a is equal to 0. Very simple. In the as in the previous, you can do the same thing. Wherever plus, you keep all the replace all the plus sign by minus sign. So everything is similar to the previous one. Finally, you will get, instead of plus, you will get minus here. That is the thing here. And as I said, these triple products are equal, and in between we have minus. They get cancel each other. Is 0. Okay. So better you take screenshot of this, work yourself. Okay.